Thanks again, everyone, for joining. And let's get into our next session on updating your toolbox for odor control, specifically for primary clarifiers. Now, superoxygenation is technology that's developed by ECO2, and what it is increasing the dissolved oxygen using pure oxygen, not air. So what we're doing is we're increasing the DO, but we're not producing any bubbles. So we're making sure that all of that oxygen gas is dissolved, and we're staying below 100% saturation level. So we're keeping all of that oxygen dissolved in the liquid, not in gas form, in bubbles. Now, historically, oxygen, the use of pure oxygen and the benefits of it have been known, and oxygen is inexpensive and highly effective, but it is difficult to dissolve. In the past, folks have tried to use different techniques and devices to make the most out of pure oxygen and its benefits, like spargers or a venturi or a U-tube, pressure tanks, nozzles, different things like that. But they all have really fairly low efficiency and poor performance when it comes to using this with raw wastewater. And then in the 90s, Dr. Speece invented the Speece Cone and it's got a very high transfer efficiency and was built for handling raw wastewater. So there aren't any things that are going to get clogged in this, like nozzles or venturis. And it also has been proven. The Speece Cone became a company called ECO2 in the year 2000. So we're celebrating 20 years in operation this year. And now we've got over 100 installations across the world. Most of them are here in the US. And the photograph on the right is a diagram of what this process looks like, where we're taking a side stream off of a conveyance pipeline. Sometimes if it's a force main in a collection system, or here we're going to be talking about actually the clarifier effluent line. So we take a side stream off of that line, go through a small pump, just to add enough pressure to overcome the system losses and back into the line. So this water then flows up to the top of the cone where it meets the oxygen gas. That gas is then dissolved into the liquid, and then it's put right back into the pipe. So before the side stream, you've got liquid with a very low DO, and then afterwards you've got that liquid with a high DO. Now this technology is used in several different applications in water and wastewater quality. So I'd like to just briefly mention a couple that we talked about earlier this summer. In June, we talked about odor and corrosion control in collection systems and at wastewater plant headworks systems. Then the month after that, we did secondary clarifier oxygenation, which is a little bit different. It's not for odor control, but it was actually to increase the BOD removal capacity of a plant by allowing the sludge in clarifiers to be oxic and act as a oxic bioreactor. This month, of course, we're going to talk about primary clarifiers and odor control. But we've got a few other applications that I'd like to just mention, and if these spark your interest, give us a call. But we've got some applications where we're adding oxygen to the effluent of a wastewater plant to meet an effluent DO permit. And the photograph you see there in the lower right is a large installation on the Savannah River, where we're improving the environmental water quality of the harbor by adding dissolved oxygen to that river while they're doing a dredging and an expansion of the harbor. So it was low quality before, and then they were going to dredge, and that water quality was going to get even worse. And so the Army Corps of Engineers selected ECO2 and the Speece Cone process to add 40,000 pounds per day of oxygen to the Savannah River harbor. And that's a photograph of that installation. We also do some applications in drinking water and other gases like carbon dioxide for lime softening or RO pH adjustment. And so now this is where I was going to turn it over to Dr. Speece, but I don't believe that I have him here with me. So, oh, Allie, you are there.
Can you hear me?
I can hear you. Wonderful. Okay, well, thanks, Dick, for joining us. I appreciate that you had a little, I posed some technological challenges having you be with us today, but I really do appreciate that. To all of our guests, this is a photograph of Dr. Speece here on the left with the Speece Cone. And he's a professor at he's been a professor at Vanderbilt University. He was in engineering. He's also an author, an inventor, a father, a husband, an all-around amazing person. And I'd like to pass it over now to him to discuss primary clarifiers. So without further ado, I'd like to introduce the one and only Dr. Speece. Please take it over.
Allie, thank you so much. I appreciate that. And we appreciate each one of you who are looking in. We're looking at a system that we feel like is a very good fit for our technology because we're looking at how can we prevent odors at a treatment plant, primarily in the primary clarifier. So as we look at the treatment plant, we see commonly the major odor source in the entire treatment plant is the primary clarifiers, which of course have the worst quality of water, the most BOD, the least DO. And so consequently, these are quite a problem. And if the primary clarifier odor can be eliminated, we go a long way to making the plant a good neighbor. So in this slide here, we see we've got a quiescent condition on top of the clarifier. So the rate of emission of hydrogen sulfide gas is not so much here, but if you get over to the effluent weirs, now we have a free fall. We've got a lot of gas exchange, and it's at these places here that this odor, which comes out at a slow rate here, now comes out at a very high rate. And so the hydrogen sulfide that used to be in the liquid now becomes the hydrogen sulfide that goes to the gas. And so consequently, we have a neighborhood problem. Next slide. So if we look at the primary clarifier, we see here that we've got 0 DO. We have essentially no nitrates. We've got a lot of bacteria because it's raw wastewater, and we've got a lot of food because it's raw wastewater. Also, we have the sulfide present, and so consequently, we have everything that a sulfide reducing bacteria would ever want in order to produce a lot of hydrogen sulfide. So in the liquid phase, we have the sulfate, the BOD, that gets converted to sulfide in the liquid phase, and then consequently, this gets transferred to the gas transfer to the atmosphere at the effluent weirs. Next slide. So this happens to be a slide of the vapor phase hydrogen sulfide at a wastewater treatment plant in Maine that Ali is going to describe a little later on. So we're looking here at the parts per million of hydrogen sulfide in the proximity of the weir at a treatment plant. And so we see here, keep in mind, 100 part per million, if you're exposed to that for very long, you lose your sense of smell. And then these concentrations here are lethal. So the amount of hydrogen sulfide that is existing in the proximity of the clarifier in this case is huge, and you can imagine the neighborhood reaction. Next slide. So one alternative is to cover the primary clarifier. And I want you to notice this manhole over here. So if you cover the primary clarifier, then you have shielded it from the atmosphere, but now you have to pull the gases from underneath the clarifier and go to a scrubber. And I recall listening to a manager at a wastewater treatment plant say once, I don't mind the cost of installing the cover, as high as that may be. The thing that bothers me most is it now is a confined space. And if I have to do any maintenance on this mechanism inside, I'm dealing with trying to find someone who's willing to go into that space and do the maintenance requirement. So the fact that it's covered solved the odor problem, but the fact that it's covered now creates what he calls an intolerable maintenance problem by covering the primary clarifier. Next slide. So if you look at the proximity of the primary clarifier, everything that's steel starts to corrode. The mechanisms in the primary clarifier corrode, the hand railing, anything that's steel outside gets corroded. It's a very corrosive gas. So next slide, please. The thing about hydrogen sulfide is the rate of corrosion compared to the maximum rate. If you have a very high concentration here, and we plot the rate of corrosion as that concentration decreases, there is reported in the literature that even at 5 parts per million of hydrogen sulfide in the gas phase, the rate of corrosion going on is about 50% of the maximum, even at these low concentrations here. So the what we would like to do is to stop the rate of corrosion rather than slow it down. So next slide. So we look at several methods. One is there are two philosophies of treating odor. One is you let the odor form, then you capture it, and then you scrub it. The other one is not to prevent the odor from forming altogether. So in the tank cover and scrub, you've got tank covers, and then you need to have some way of scrubbing that. When we look at chemicals, you could add nitrates, which would support the bacterial growth of oxidizing the sulfide, or you could have iron salts, which precipitate that. And the issue we're going to suggest here is putting in dissolved oxygen so that the hydrogen sulfide never forms and we prevent its formation altogether. Next slide. So here are some slides. Here is one alternative is to just cover the circumference of the primary clarifier where the weirs are, and then to suck the gas out underneath these covers here so that the main part of the tank is left open, but most of the odor which is formed here gets sucked out and goes to some kind of a scrubber. Here's a scrubber not for the primary clarifier, but for another section of the plant. So the gases go in, and either you have a caustic scrubber or some chemical to oxidize or precipitate the sulfide. Here would be a view in which they've got a domed cover, an entrance inside, and then the gases get pulled out and sent to some kind of a scrubber. Next slide. So we look at the cost and we say the cost of alternatives, you've got, we can use pure oxygen, we can raise the pH using caustic, we could put in hydrogen peroxide, we could put in chlorine, we could put in iron or magnesium oxide, or we could put in nitrates. And so the point here, we've got oxygen is low in cost, but it requires expensive equipment to dissolve it. And so we'll look at the next slide. If you take nitrate, for instance, nitrate is not nearly as oxidizing as dissolved oxygen. And so nitrate cannot chemically oxidize sulfide, but it can support microbial oxidation of the sulfide. Nitrate has a relatively low sulfide oxidation rate, about 20% of that of dissolved oxygen, and that gets translated into the fact that it requires about a couple hours after you put in the nitrate before the bacteria eat much of the sulfide, versus it takes about 20 minutes, 20 to 30 minutes if you raise the dissolved oxygen for the combination of chemical oxidation plus bacterial oxidation to eliminate that hydrogen sulfide. Likewise, it's not economical to achieve a dissolved sulfide concentration less than about 0.5 milligrams per liter. And so the 0.5 milligram per liter is able to support corrosion, and it has a significant odor potential. So nitrates will reduce the odor and reduce the corrosion, but we're looking at dissolved oxygen to actually eliminate the hydrogen sulfide. Next slide. Now I'll turn it over to Ali on the cost comparison in these examples. Thank you.
All right, thank you so much, Dr. Speece. Again, it's just really a pleasure to have you with us and to get your insight. Some of those things that you were telling me about the covers, I really didn't have any idea. I hadn't thought about confined space and the intolerable maintenance. So thank you very much. I'm going to take over and talk about a few examples of these three control methods that Dr. Speece just laid out. And the first one is a newspaper article that I found, and it's from the Bowery Wastewater Treatment Plant, which is up in New York, around New York City, in the town of Astoria. And so I found this article where they spent $3 million for a project to cover 4 tanks that were about 85 feet in diameter. They also used dual bed carbon filters. This was a slightly different application, but the cost is going to be pretty relative. So I divided that capital cost and got the number of $825,000 as the cost to cover and scrub 1 tank. So $3 million for 4 tanks. So that's per tank. Plus you've got an operation and maintenance expense that is ongoing. It wasn't identified or laid out clearly here, but I'm sure there is an expense for maintaining those carbon filters, as well as a limited life expectancy for the tank. And then again, the confined space. So there's an example of covering and scrubbing. And I also would like to show you an example of a chemical feed. So this is the chemical analysis of what was used at that same application I'm going to talk about in Maine, where they do have the superoxygenation. So it's going to be a direct comparison for financial analysis. So when Madison, Maine did a trial for bioxide, and when they were contemplating different options for controlling odors, they've got, this above ground primary clarifier that you can see in that upper left-hand corner. It's 90 feet in diameter. Their flow through the plant is about 4 mgd, just to give you a little perspective of size. This is a Woodard and Curran operated plant, and they also were doing the design for the upgrade. And they had really high H2S at the effluent weir, just like Dr. Speece was saying, and they live in this adorable little community in Maine. So they had a lot of odor complaints, and they needed to do something. So they started feeding bioxide, and they estimated a dosage of 200 gallons per day. Well, that was not effective. And so the actual dose was 350, over 350 gallons per day. So when you take the cost of this, it was bioxide at about $2.50 per gallon. So that was $325,000 per year to do the best job that they could, which was effective odor control, but we still weren't able to get to 0 dissolved sulfides. Now, there was not a capital expense required with this, but this is an ongoing expense that really you can never expect it to go down. So it's $325,000 a year for this option. Now let's compare that with what the oxygen system looks like. I'm sorry, I think I misspoke. 325 for bioxide feed. Now, alternatively, this is what the oxygen costs are. So they had to run a capital project and install this Speece Cone in the oxygenation system. But oxygen is very inexpensive to buy or to make it on site, and it's about 5 cents a pound. It's about 1/10 the cost of calcium nitrate. So we calculated the dose of dissolved oxygen that we needed to put in to maintain aerobic conditions throughout the hydraulic retention time of the clarifier. And it was 35 milligrams per liter of DO was required. And that calculates out to 1,250 pounds per day of oxygen. So the cost to operate this oxygenation system is only $20,000 per year. And that includes the electricity to run the pump, the electricity to make the oxygen, the maintenance and operation of the system. It's only $20,000 a year compared to $325,000 with calcium nitrate. But again, oxygen is great and cheap, but it's a little difficult to install. So that's where ECO2 comes in, and we worked with Woodard and Curran to design a system. And with engineering, installation, and equipment, it all came to $800,000 total project installed. So with the same parameters that I just described for dioxide use, they're saving $300,000 a year, which was a 2.4-year payback, which was sufficient for Woodard and Curran to move forward quickly. And also they are getting much better results. They're getting 0 H2S at the effluent weir, as shown on that odor logger in the bottom photograph. Now, when we put that oxygenation system in, we were taking a side stream off that primary effluent and going through the cone and picking up the dissolved oxygen. And this is a photograph of that dissolved oxygen meter on the effluent of that cone. So the raw water was coming in and coming out with 62 milligrams per liter of oxygen at the cone discharge. And then that was blending with the rest of the primary clarifier effluent flow and making its way through the retention time of the clarifier and then going over the weir. And at the weir, the DO measurement is 12.4 milligrams per liter. So we still have aerobic conditions at the effluent weir. And the next photograph there is again just showing that you've got 0 H2S at the effluent weir. I would show you a graph, but it's hard to graph consistent 0. It's just a flat line at the bottom of the chart. So hopefully this graphical or this photographical representation will just kind of show you, you boost the DO at the beginning, but you stay under saturation, so there are no bubbles that come out, and the flow characteristics in the tank were exactly the same, and they established aerobic conditions throughout the entire clarifier. So this is a drawing of the project plans. So here in the bottom right corner of this diagram, you can see they had the headworks influent chamber and pump station. So they're able to pump this flow with the existing pumps shown here in the upper left. They pump that flow through the cone, pick up the oxygen, come back, blend, and go into the clarifier for its natural settling process. So we've just added a small loop on this feed line to increase the dissolved oxygen level. And there's the Speece Cone sitting next to the primary clarifier at grade. And so they were able to use the existing pumps for the primary clarifier effluent and just raise the head enough to get through this system and back into the line. Now this photograph here is a picture of their oxygen generators, which were purchased by a company called PCI. So this was a little bit separate from the Speece Cone part of a scope of supply, if you will. Now there's two options of getting the oxygen supply, and they decided to make the oxygen on site as opposed to having a tank and taking bulk deliveries. I'll show you what that looks like in a minute, but this last photograph is just a view from the clarifier walking bridge, and you can see that the quiescent conditions in the clarifier are not interrupted even with the addition of dissolved oxygen. So I mentioned oxygen supply. You've got to get this oxygen gas at relatively pure concentrations. And then what the Speece Cone does is dissolves that into the liquid. So instead of going with the oxygen generator, which there are a couple of manufacturers of these generators, but they require maintenance and they're a capital expense. And they're noisy and they require some other installation considerations. The alternative that anyone can evaluate is purchasing liquid oxygen, because there's no capital cost with this, but there's a monthly lease from a local supplier like Airgas or Praxair. And you see those trucks driving down the road. Well, they make large trucks and small trucks, and depending on the size of the installation, they back in and fill this tank, and then this is just piped over to the ECO2 system to be dissolved. So that has no maintenance, no noise, no capital, but you do need truck access. So those are the two options for oxygen supply. Now, just quickly, I'd like to wrap up with how we determined what size to put in up there at Madison, or really anywhere. And the fact is that you need to calculate the oxygen demand, because we're trying to just satisfy that oxygen demand. So to determine how much oxygen you need for a specific application, it's all about the time, the retention time, and the oxygen uptake rate, which has a standard rate of 10 milligrams per liter per hour times the flow. So here in Madison, we had 3 different flow scenarios: low, average, and peak. And so you can see that when there's a lower flow, we've got a higher retention time, 5 hours times 10 milligrams per liter per hour of DO usage, 8.34 pounds per gallon, and the flow rate of 2.7 mgd. So I get a dosage rate here, so I need just over 1,000 pounds per day of oxygen. Well, the way the math works out, as the flow goes up, the HRT goes down, and so you have a fairly proportionate number even when the flow goes up, because the retention time goes down. Now, I'd like to just show you the economics of this project, and then we'll wrap up. So here in this column, I've got the costs associated with the superoxygenation for odor control by adding pure oxygen with the ECO2 system and the Speece Cone. And then in this column, I've got the cost for the nitrates, which really there is no cost except for the chemicals itself. There's no capital or installation costs there. So by the time you add together the cost to make the oxygen and to power the pump, it's about 20 grand per year. Also, they had an aeration savings that was observed. Because they're feeding oxygen in the primary clarifier, less oxygen is required in their aeration basin. So they were able to turn down their blowers and have a significant savings there. Now we've got an ECO2 and the PCI generators. The capital cost for that was $320,000. Installation engineering, $470,000. So those two together, that's where I got the $800,000. $800,000 in capital to save $320,000 a year. That's where the 2.4-year payback came from. And that was very good for Woodard and Curran, and they're still operating today. And I'm sure that they wouldn't mind taking a phone call from anyone who is interested in learning a little bit more directly from the user. But in conclusion, we're able to add dissolved oxygen and have no impact to settling, which is required in the clarifiers. We've got a couple other case studies on doing this similar thing. So this is not just a one-off, but we do have case studies available. It's also highly efficient. We're getting over 95% oxygen transfer efficiency, and we're feeding it to meet demand. So we basically flow pace the oxygen feed rate. We're saving a bunch of money. We're reducing the aeration requirement, and we're getting almost consistently 0 H2S levels, but less than 5 across the board. Now, to give credit where it's due, Dale Clark is the manager up there at the Woodard and Curran plant in Maine. So I'd like to thank him for providing us with the data and the pictures and everything. Also, Kevin Jacobs is our longtime ECO2 champion, engineering director, and he has put together a lot of this information for us. Also, we've got some resources for you to take away. There's some case studies and a technical paper that are available as a handout. Actually, one's a case study and one is a magazine article that was written by the engineer of a project. So I invite you to download the handouts in your control panel on the right-hand side of the screen. Also, look for that follow-up email from us with this presentation file and a link to a recording that you could share this with anyone else that might be interested. Also, let us know if you're interested in receiving a customized certificate of completion for this half hour that you can use for continuing education credits. And also, we've got our website, eco2tech.com/news, is where we've got a bunch of new videos, case studies, some really fun new digital content coming in the next month before WEFTEC. So I invite you to reach out and think about what superoxygenation might be able to do for you. I'm going to put some contact information up on the screen. Again, my name is Allie Trollier, and I'm in Florida covering the East Coast, and my colleagues are there listed as well, Ryan and Clay. So please reach out to anybody at any time. We'd love to talk to you about water or wastewater. And I did say earlier that we would invite some questions, and I know we're getting to the end of our 30 minutes, but we do have a couple of questions here, and I'd like to just take a minute since we've got Dr. Speece on the line and just say, he says, this is a question about what is the range of influent dissolved sulfide concentration in the Maine example arriving at the headworks? Okay, so this was saying, Dick, I'm not sure if you recall, I may need to follow up privately on this one, but the dissolved solids coming into the plant at Maine, do you recall if that was high or if they were really just more concerned with the sulfide formation within the clarifier itself?
I would think it's both, but the contribution coming in, I would think would be a major part of that, as that component as well. I can't give you that concentration coming in. I would assume it might be in the range of something in the order of dissolved in the liquid, something in the order of, say, maybe 40 milligrams per liter of dissolved hydrogen sulfide coming in, and then more gets formed as it cooks in that clarifier.
Right, okay, so we might say if you're looking at protecting the headworks, one might need to dissolve the oxygen upstream of the headworks, because if you've got it already coming into the headworks, by the time it goes through maybe some of the grit or different headworks devices, you may strip some of that H2S off. So by the time it gets to the clarifier influent, I'm thinking maybe some of those dissolved sulfides are already stripped out. Would that be correct?
Yes.
Okay.
Yes.
So in these primary clarifier applications, we're mostly concerned about that anaerobic retention time within the clarifier to protect the odors coming from the effluent weirs. But we also have a lot of installations where we're treating the headworks by dissolving oxygen in a upstream pump station to allow that 30 minutes of contact time for the oxygen to do its job before it hits the headworks, where it may come out of solution. The H2S would come out of solution. So, all right, thank you so much. Here, we've got another question related to that graph on corrosion rates. The question is, does the H2S corrosion and concentration rate curve for the exposed concrete follow the same pattern shown for steel? So is that graph good for concrete and steel?
I would assume they're quite similar because the corrosion takes place when the bacteria, if the H2S comes into an oxic environment, if there's moisture there, the bacteria then will oxidize that to sulfuric acid. And I think the sulfuric acid is the main corrosion component, even though the H2S is corrosive as well. But the real kicker comes when the bacteria, it's like in the crown of a sewer, these amazing bacteria that can live at a pH of battery acid are generating battery acid for that concrete sewer, or for once it gets out to a surface where it's exposed to oxygen, where these bacteria can oxidize sulfide to sulfuric acid.
Okay, and so sulfuric acid has a fairly similar corrosion rate for concrete and steel.
I would say they are similar, yes.
Okay. Okay, fair enough. I like it. I'll buy it. Okay, now we've got another question here about organosulfide components. Let's see here. I can make this a little bigger. Okay, here's the question. Any experience using oxygen to prevent formation or actually remove odor-causing organosulfur compounds? Excuse me. Organo. I'm sorry, there's one more little comment here, Dick. It says, thinking species like dimethyl sulfide or mercaptans, not necessarily just H2S.
Yes, there's a very interesting study done years ago in which oxygen was added, and they analyzed for the mercaptans and the other odorous compounds, and those likewise were either chemically or microbially oxidized once the dissolved oxygen became positive. So the answer to that is a clear yes, that the skatols, the indoles, the mercaptans, as well as the inorganic hydrogen sulfide, those are all very good substrates for bacteria, and oxic conditions allow those to be taken out just like the hydrogen sulfide.
Wow, thank you for that excellent question. I promise that was not prepared. That was off the cuff. I don't think I could have done that, but I think we mostly talk about H2S because it seems to be the major component of odors, and it's the easiest to measure. Is that true?
It's easiest to measure, that's true, but sometimes it's not the most odorous thing there. And so that's why this question was quite important, because getting rid of the hydrogen sulfide may not get you home. And with the use of oxic conditions, you also get rid of these other extremely odorous compounds in the process.
Excellent, wonderful. Well, that brings us to the end of our questions. And so I think, Dr. Speece, I think that we're good for now. And if we receive any other questions, I'm really excited to answer any of those individually, and we can pull Dr. Speece in whenever necessary. So everyone, thanks so much for joining us today. Please look for the handouts and the video link, share it with anybody you know, and give us a call anytime to discuss more about odor control or other water quality and wastewater oxygenation applications. Thanks so much, everybody.
Thank you.